Okay, so we're ready to again kind of move on here, but just to review here and make sure we understand where we're at, the kind of result we have here, let's look at time domain here. And then frequency domain. And I'm going to just make one exception here, that the initial conditions all 0. So the time domain here, remember we have a resistor here. Whoops. We have plus minus V at t. We have a resistance, and we have a current I at t. And then in the frequency domain, well, we have a resistor still, and it's just resistance of R, and we just still have plus minus V at S, and then the current I at S. Then for the time domain for an inductor, remember we still just have my normal inductance, plus minus V at t, current I at t. And then in the frequency domain, again assuming the initial conditions are 0, we wind up with an inductor that is S times L as far as the inductance, plus minus V at S, and the current here is I at S. And then for the capacitor, of course, we have in the time domain plus minus V at t, some capacitance C, and some current I at t. Then in my frequency domain, I have a capacitor, but the value of the capacitor is now 1 over S times C. And then, of course, I've got plus minus V at S, and my current I at S. Alright, so this is kind of where we left off, but I want to point out a couple things here before we move on that are quite important. So the reason we're going to be able to just kind of do some algebra is let's look at what we have here in the Laplace domain. And now again, this is assuming all initial conditions are 0. We will look at some examples where they're not, but we're going to start with initial conditions being 0. What do we have here? Well, we have V at S is equal to R times I at S. Okay, so this is just Ohm's Law. Right? Our standard Ohm's Law. Now, if we scroll back up here on some of the previous ones here, whoops, a little too far. Remember we had V at S is equal to SL times I at S. So if we go down here to where we are, what we have down here now is that V at S is equal to S times L I at S. But now look at this here. We have this S times L, which is kind of my inductance now in the frequency domain, and I have an S times L here. So this is also an Ohm's Law, I'll put it in quotes, relationship. And then if we write one more equation down, we could scroll back and see it, but if we write the equation down for the capacitor, we have V at S is equal to 1 over S times C times I at S. Well, again, if we look at it here, I've got this 1 over SC here as kind of my capacitance in the frequency domain, and I have the 1 over SC here sitting in front there. So this is also an Ohm's Law quote type relationship. But it gets even better than that, because okay, we have more formulas to memorize. No, we don't. We really don't. Because this should look familiar to us, because when we did, referring back to steady state analysis, we had, V is equal to Z times I, where if it was a resistor, that was just equal to R, If it was an inductor, it was equal to j omega L. And if it was a capacitor, it was equal to, well, technically, when we first derived it, it was equal to 1 over j omega c, which we then typically wrote as minus j over omega c. But then let's think about it. Remember, in the previous lesson, we said that, hey, well, we're not going to go through the theory on why we can do this, but we can let s equal j omega. And wait a minute. If I do that, s being j omega, look what happens when I plug it in here. I get, well, first off, for r, I'd get, quote, zr is equal to r. I'd have zl is equal to s times l. And then, well, doing it here, seeing that the j omega is in the denominator here, we'd have, quote, z for the capacitor being 1 over s times c. So we still have this kind of Ohm's law, and I'll put in quotes here impedances, because the impedances are really for steady state analysis, but we can kind of view it the same way. And so that's why when we look at Laplace transforms, we can just do a simple algebra circuit analysis. So let's look at an example here on how we can do this here. So this is a very simple example to start with. So it's not a complicated example. So some of the numbers are kind of messy, but it's not a complicated example. So we've got a voltage source that's 20 U at T. We have a 250 ohm resistor. We have a 250 millihenry inductor. We have a 16 microfarad capacitor. Okay, so we now have to kind of go through and do all the work here. Now, I'm going to first transform everything into the S domain. So this would just be 250. Now if I do this into the S domain, I'd have 1 over, sorry, not 1 over. For the inductor, I'll even write it as ZL. I'd have S times L, which would be S times 250 millihenry. But I'm just going to write that 250 is just 0.25 S. And then the 16 microfarad is one where we have to do a little bit of work here. So this would be 1 over S times C, which would be 1 over S times 16 microfarad, which, if you do that, yeah, it kind of gives you a pretty big number. It gives you 62,500 over S. So I'll have here 62,500 over S. Now, the other thing we have to do here when we're doing circuit analysis is we have to look at the voltage supply here. That's 20 U at T. So I have to do a Laplace transform of that, and that's again where we want to keep our Laplace transform tables handy, because I need to say, well, what's the Laplace transform of U at T? That's 1 over S. Okay, so I would come back and say, okay, well, this would be then 20 over S. So now my entire circuit's in the Laplace domain. And, well, I should tell you what we're looking for. I haven't told you what we're looking for. We're looking for V out at T here. And I'll also say here, all initial conditions are 0. Because as I said, the first couple examples we're going to look at is where all the initial conditions are 0, just to make life a little bit easy. We'll look at more complicated examples where they're not 0 later on, but it's really just more algebra you have to do. It doesn't make it more difficult, it's just more algebra. Alright, so all initial conditions are 0. And I'm trying to find this V out. Well, I can do the same circuit analysis techniques that I've done before, so I'm going to look at doing just voltage division. And so if I do voltage division, what that would mean is that V at S, V out at S, is equal to, well, it's 62,500 over S, because that's the circuit element we're looking at, divided by, well, this is series, so I would add everything up, 250 plus 0.25 S plus 62,500 over S, and then I have to multiply by my input voltage, which would be 20 over S. Now, we're going to have to multiply all this out here, but we want to sometimes make a little bit of, what I'd say here, be careful as far as thinking about this problem in the correct way here. So what I mean by that here is I'm actually going to rewrite this. V out at S is, I'm going to do 20 times 62,500 over S divided by S times 250 plus 0.25 S plus 62,500 over S. Now, why am I doing it like this? Well, remember, at the end here, just like we did in some of the previous lessons, we're going to have some f at s. In this case, it's v out at s. And we're going to have to do a partial fraction expansion to get back to the answer here. And so, since I'm multiplying by 20 over s, and this s is in the denominator, it doesn't make any sense to multiply through by it, because that's going to be something I could factor out in the end. So why would I multiply through by it? So that's why I'm going to leave it out in front. Okay, but now we do have to simplify this sum here, because I do have an issue where I've got a complex fraction. So to get rid of the complex fraction, of course, I would multiply the numerator by s. But then if I do that, of course, it means I have to multiply the denominator by s. And you might say, well, you've already got an s there. Trust me, this is going to make more sense. This is the proper way to do it. Okay? Well, then I'm going to go ahead and do 20 times 62,500. So we get V out. V out is equal to 1,250,000. And again, this is where we just have to kind of keep track of the numbers appropriately, over S times, and then here, okay, well, I'm going to multiply, I'm going to take this S, multiply it in. So I'd have 250 S plus 0.25 S squared plus 62,500. Okay, so we got that now. Now what we want to do is factor this. And this is where, you know, having a calculator that can do some of this factoring for you, it can save you some time, basically. It's not that you absolutely need it, but it can save you some time. Now, one thing I'm going to do here right away here, because I'm going to go ahead and just do it by hand here. I'm going to write this as 1,250,000. Apparently I'm writing it in blue. Over S. And I'm going to bring out, I'll put this in front. That looks like a 5. I'm going to factor out in the denominator here 0.25 times S. And the reason is then I'll have S squared. Okay, if I factor out a 0.25, I got to do 250 divided by 0.25, which would be plus 1,000 S, plus then I got to do 62,500 divided by 0.25, which would be 250,000. So that's what I've got so far right now. And again, it's this problem, as I said, the only roughness about it is that, well, we do have some large numbers that we're having to deal with. So I'm going to now take this 0.25 into the numerator, so that basically means multiplying by 4. So this would be that V out would be, and I'm just going to double check my arithmetic just so I don't make a silly mistake. Yeah, so this would be 5 million over S, and then if I look at this and stare at this long enough, or use the quadratic formula or whatever, this right here factors to S plus 500 quantity squared. Now we haven't done a partial fraction expansion like this yet, so that's kind of why I wanted to look at this one. So we now have my answer. As a side note, this is the answer. This is V out in the S domain. Just like on the previous examples we had done where I had f at s, that was my output. Well, here's my output. That's why I wanted us to practice that partial fraction expansion. Because, okay, now we have to do that partial fraction expansion if we want V out in the time domain. Now, what we need to look at here is this is still a linear term. And it's a linear term because we have no s squared. But it is what's called a repeated term, or often we like to refer that as to a repeated root. Now, if we go back to the Laplace transform table again, look at right here. Hopefully you can see my cursor circling around it. I have something where I have 1 over quantity s plus a squared, and I get something that is t e to the minus at. So we do have something in that form, so that's good, but we have to make sure we do our partial fraction expansion correctly. And if you recall partial fraction expansion correctly, and if you don't remember how to do it, we've done several on the examples, but there are plenty of websites out there, YouTube videos that can show you how to do partial fraction expansion and show you all the different cases for partial fraction expansion. So what we'd have here is V out. Well, I have my S term here, so I'd have A over S. But then for repeated roots, we'd have B over S plus 500. And then we have plus C over S plus 500 squared. And that's how you do repeated roots. Now, just as a side note here, if we I'll put it here, if we had S plus 500 cubed, you would have another term plus D over S plus 500 cubed. You know, you would still have this 500 squared, and then you'd have the 500 cubed, and so any kind of time you have a repeated root, you're just going to have more and more terms that are added. But we don't have that here, so we don't need to include that, so let's erase it. And then, of course, we know that this is equal to 5 million over S times S plus 500 squared. And then again, rewriting this as far as partial fraction expansion goes, you'd get 5 million is equal to A times S plus 500 squared plus B times S plus 500 plus C times S. Now we do have some nice numbers we could pick. First nice number I would pick is just S equals negative 500, because that will kill the A and kill the B, because this term will be 0 here and this term will be 0. And so if I get that, now there's nothing to plug in on the left hand side, so I'm just stuck with 5 million here. 5 million is equal to 500 times C. And then, of course, we do that, we get that C, negative 500C, and we get that that's equal to negative 10,000. So we figured out C. Great. Now we need to figure out another one. Another easy number that hopefully you guys can see pretty quickly would be S equals 0. Because if I do S equals 0, it actually kills out both the B term and the C term, and so I'm left with just A. So I'd have 5 million is equal to A times 500 squared. And then going through that, you would get A is equal to 20. Now to find C, or not C, we have C, to find B, well, we know A and C at this point, so we just pick another number for B. Now, often, as I said in other examples, we've picked 1. And we could do that, and it would work just fine. I want to show you another thing that you can do sometimes that, it seems like it would be odd to pick this, but it can sometimes lead to numbers that are a little bit nicer. There'll be bigger numbers, but it can still actually not be bad in the end here. Is instead of picking s equals 1, I'm going to pick s equals 500. You might say, well, why am I picking such a big number here? Well, you'll see why in a second. So instead of having 501 squared, I'm going to have 5 million is equal to, well, A is 20, and then 500 plus 500 is simply just 1,000 squared, and then it would be plus B times 500 times 1,000 is equal to, not equal, I forgot the C, minus 10,000 times, and what would it be here, 500. You might say, well, these are going to be big numbers. Yeah, they are, but it's going to be simple just to add and subtract on my calculator here, because I'm not even going to multiply anything out. I'm just going to simply write then that B is going to be 5 million minus 20 times 1,000 squared plus 10,000 times 500 divided by 500 times 1,000. Now you might say you could do the same thing if I had just used 1, and you're absolutely right. You could have done the exact same thing if you had used 1. But I'm just showing you don't have to use 1. You can pick any number. And if you guys use 1, maybe go ahead and use 1 and see what you get. Because if you use s equals 1, you should still wind up with b equals negative 20. And so then if we look at what the partial fraction expansion is then that we have here is we have that v out at s, oops, I want to be this in black, v out at s is equal to, well, I'm going to have 20 over s minus 20 over s plus 5 minus 10,000 over, I'm sorry, s plus 500 over s plus 500 quantity squared. And now again, going back to our Laplace transforms, we have all those. 1 over s we know is just u at t. S plus 500 is just going to get me e to the minus 500. S plus 500 squared, which is this one right here again, that's going to get me t e to the minus 500t. And so doing my inverse Laplace transform, we're going to have 20, and I'm not writing 20 u at t because remember what I'm going to do, I'm just going to multiply everything by u at t at the end. So 20 minus 20 e to the minus 500t minus 10,000 e minus 10,000 t e to the minus 500t, and then all of this multiplied by u at t. Now, we said that this gives me, and I know this video is running really long, I apologize for that. We said that the Laplace transforms gives us both transient and steady state. Well, look here, this portion right here is the transient response. So, and if you think about it, t equals 0, we get that the voltage is 0, because the initial conditions are 0. But this is the transient response, and we can tell that because as t goes to infinity, I'm just going to do these light dots here. As t goes into infinity, this is going to go to 0, and this is also going to go to 0. So as we go for time going to infinity, in other words steady state, these two terms are going to go away. So that's my transient response. And then right here, well, the 20, there's no like e to the minus t or anything like that. This is going to be my steady state response. And if we go back to the original circuit, we can kind of see that makes sense. This is actually something we had analyzed in the previous semester. The way we wrote it, instead of doing 20u at t, we had instead, we put a switch in here and said that, well, the switch closes at t equals 0, and we found out everything using differential equations, because this is a circuit we did last semester using differential equations. But now what we've done here is that we've analyzed that same circuit and done it using Laplace transforms, and not only, whoa, something happened here. Well, I'll end the video here so we don't have to worry about what's going on here. We can see here using the Laplace transforms, we were able to get both the transient and steady state. So we'll pick up here with some more examples in the next set of videos.